Alright, welcome back everybody. In this video we are going to talk about content related to section 10.11 from AP Calculus BC, finding Taylor polynomial approximations of functions. In this lesson, which is going to probably span at least two, maybe three videos, we'll see. In this lesson we're going to focus on three primary topics. One, what the general form of a Taylor polynomial is and how to write the Taylor polynomial for a given function. 2, what the general form of a Maclaurin polynomial is. It's a specific type of Taylor polynomial, by far the most commonly used of the Taylor polynomials, and how to write the Maclaurin polynomial for a given function. And number 3, how we can determine the coefficient for any term of a Taylor polynomial without having to write out the entire polynomial up to that term in order to get that particular term. All right. A little bit of a bridge here. It says, in other words, we're going to spend a lot of time figuring out how to write functions as approximating polynomials. Well, why would I want to do that? Well, if you think about it, of all the functions that we've encountered in our mathematical lives up to this point in time, polynomials are by far the easiest to work with, the most predictable, the easiest to work with in pretty much every respect. So if we can approximate other functions, which are much more difficult to deal with, using polynomials, it enables us to work with those functions or approximations of those functions in a form that is considerably easier for us to work with or easier for us to manipulate. So let's go ahead and we're going to get started here by looking at the process that we'll use for developing polynomials, and we're going to motivate this with an example. All right, our first example. We are going to construct a polynomial p of x equals a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub 4x to the fourth that has all of the following behavior at x equals 0. We want the polynomial at 0 to be equal to 1. We want the derivative of the polynomial at 0 to be equal to 2. We want the second derivative of the polynomial at 0 to be equal to 3. We want the third derivative of the polynomial at 0 to be equal to 4. And we want the fourth derivative of the polynomial at 0 to equal 5. This kind of seems like it might be difficult for us to do at first glance, but it's actually relatively simple, again, because of how predictable polynomials can be. First of all, we know the original polynomial p of x. And so in order to find p of 0, we're just going to put 0 in here everywhere where there's an x. And if you look at what happens when we do that, p of 0 is equal to a sub 0 plus a sub 1 times 0 plus a sub 2 times 0 squared plus a sub 3 times 0 cubed plus a sub 4 times 0 to the fourth. And that whole thing is equal to just a sub 0 because all the other terms drop out. Well, remember, we wanted p of 0 to be equal to 1, and so therefore we can gather from this that we want a sub 0 in our polynomial to be equal to 1. And so we have the first piece of the polynomial that we want. All right. Now, we want the derivative to be equal to 0 at 2. Well, let's go ahead and take the derivative of p of x and find out what p prime of x is equal to. So p prime of x, the derivative of the constant is 0. The derivative of a sub 1x is just going to be a sub 1. The derivative of a sub 2x squared is going to be 2 a sub 2x. The derivative of a sub 3x cubed is going to be 3 a sub 3x squared. And the derivative of a sub 4x to the fourth is going to be 4a to the fourth, or pardon me, 4a sub 4 x to the third. So then, p prime of 0 is equal to, again, I'm not going to write it all out like I did it for p of 0, but this term and this term and this term are all going to be 0. So p prime of 0 is equal to a sub 1. We also want p prime of 0 to be equal to 2, and so from this we can glean the information that a sub 1 is equal to 2. All right, next, p double prime of x is going to be the derivative of p prime, so that's just going to be 2a sub 2 plus 6a sub 3x plus 12a sub 4 x squared. And so p double prime of 0 is going to be equal to 2a sub 2. Well, we also want that to be equal to 3 in order to match the polynomial that we want. And solving for a sub 2, that gives us that we want a sub 2 to be equal to 3 over 2. All right, continuing on. P triple prime of x. Again, the derivative of the constant is 0. This is going to be 6a sub 3 plus 24a sub 4 x. And we want p triple prime of 0 to be equal to 4. And so a sub 3 is going to be equal to, and I'm going to leave this as 4 over 6. I hope you don't mind. And then we're going to take the fourth derivative. I'm exhausted from all these derivatives. And we get that the fourth derivative is 24a sub 4. And so the fourth derivative at 0 is going to be 24a sub 4. We want that to be equal to 5. And so a sub 4 is equal to 5 over 24. All right, so our polynomial is going to be 1 plus 2x plus 3 halves x squared plus 4 sixths x to the third plus 5 24ths x to the fourth. And that polynomial matches all of this initial behavior that we want to have happening when x is equal to 0. Now I'm going to rewrite this polynomial. If you're really a student of numbers and you see how numbers evolve, you should notice that these denominators of our fractions, and if you were really paying attention to where they were coming up from as we were taking these successive derivatives, you'll recognize that these denominators are all factorials. And so in fact, this is 1 plus 2x plus 3 over 2 factorial x squared plus 4 over 3 factorial x cubed plus 5 over 4 factorial x to the fourth. We might be onto something here. All right, let's go over to the next page and I will pull away the curtain. The definition of the nth Taylor polynomial and the nth Maclaurin polynomial. First, the Taylor polynomial. If a function f has n derivatives at x equals c, then the polynomial p sub n of x is equal to f of c plus f prime of c times the quantity x minus c plus f double prime of c times the quantity x minus c quantity squared all over 2 factorial up to the nth term. That's going to be the nth degree polynomial, whatever n is. N could be 2, and the polynomial could stop right here. But that's going to be the nth degree Taylor polynomial. If c equals 0, when c equals 0, it gives us this form instead, f of 0 plus f prime of 0 times x. That would have been x minus 0, but it's just x. Plus f double prime of 0, x squared over 2 factorial, etc., up to the nth term. This is the nth degree or nth order Maclaurin polynomial. So Maclaurin polynomial is just a Taylor polynomial at x equals 0. Okay? We can shorten up what both of these look like by writing them as summation notation. The Taylor polynomial at c is the sum from 0 to n of the kth derivative of c times the quantity x minus c to the kth power all over k factorial. The Maclaurin polynomial, the nth degree Maclaurin polynomial, is the sum from 0 to n of the kth derivative of 0 times x to the k all over k factorial. So those are our general forms, and the only way you're really going to get these under your feet is by using them and getting a lot of practice in. So that's what we're going to start doing now, is we're going to start doing some examples. We'll start here with example 2. We're finding the fourth degree Taylor polynomial for f of x equals the natural log of x centered at x equals 1. So let's talk about what this general form is going to look like. First of all, it's centered at x equals 1. That means 1 is our c value. Okay, so in essence, what we're looking for here, our fourth degree polynomial, and I'm going to do this since this is our first example. Our fourth degree polynomial is going to be f of 1 plus f prime of 1 over 1 factorial. I don't need to write that. That's over 0 factorial, which is 1, over 1 factorial, which is 1. I don't need to write either of those. Times the quantity x minus c, which is 1, plus the second derivative, the second derivative at 1 times the quantity x minus 1 squared, all over 2 factorial, plus the third derivative at 1 times x minus 1 to the third, over 3 factorial, plus the fourth derivative at 1 times x minus 1 to the fourth, over 4 factorial. And so we've got almost everything we need to write the polynomial. Look at all the things that we already know in this form. We know this x minus 1 here. We know this x minus 1 squared in the 2 factorial. We know this x minus 1 to the third in the 3 factorial. We know this x minus 1 to the fourth in the 4 factorial. So all we need is the value of the function and its derivatives at x equals 1. So we're going to go ahead and start finding those. Our function is f of x equals natural log of x. So f of 1 is the natural log of 1, which is 0. Then I find f prime of x. The derivative of the natural log of x is 1 over x. So then f prime of 1 is 1 over 1, which is 1. F double prime of x, I take the derivative of 1 over x. It's going to be negative 1 over x squared. So then f double prime of 1 is negative 1 over 1 squared, which is negative 1. And then f triple prime of x is going to be 2 over x cubed. So f triple prime of 1 is going to be equal to 2 over 1 cubed, which is 2. And finally, the fourth derivative of x is going to be negative 6 over x to the fourth. So the fourth derivative at 1 is going to be negative 6 over 1 to the fourth, or negative 6. And so now we can just go ahead and fill these values into our polynomial, our fourth order polynomial for natural log of x. F of 0 is 1. F prime of 1 is 1 times, so this is going to be 1 times x minus 1, plus f double prime of 1 plus f triple prime of 1 plus f to the fourth prime of 1 and if I clean this up, this is just going to be quantity x minus 1 minus quantity x minus 1 squared over 2, because 2 factorial is 2, plus, and 3 factorial is 6, so 2 over 6 is going to be 1/3, so this just becomes x minus 1 cubed over 3, and 6 over 24 becomes 1 over 4, so this becomes this polynomial. And there is our first Taylor polynomial. Now, it says here, now is a good time for us to pause and examine what's going on as we build these polynomials and how they compare to the actual functions that they're approximating. At this time, we're going to look at the graph of y equals natural log of x and the first several Taylor polynomials centered at x equals 1 to see how they compare to the graph of y equals natural log of x. Unfortunately, I'm a little bit short on time and won't be able to get that in, so we're going to go ahead and start the second video by looking at these graphs. And then we'll continue from there. All right, so that's the end of our first video on section 10.11. See you next time when we continue on with a little bit more on Taylor and Maclaurin polynomials.